Thank you. So, today we're going to talk about playing games with the help of the computer. So, we're going to teach the computer to play games. Which topics are we going to touch on? We're going to touch on, first, a very simple game to explain the mechanic. Then we're going to look at noughts and crosses. Then we're going to play some chess. And finally, we're going to take a look at the game of Go. So, I want to play a game. So, what kind of game could we start with, which is the most simple game to actually explain what we're going to do? For this game, I'm going to use a tree structure. You always start, and if you get the higher score, you win. So, what does a tree look like? Well, a tree is very simple. It's a node with some connections to other nodes. So, this game is very, very simple. You are the player, you get to pick. Which one do you pick? 5 or 3? You obviously pick the highest one. You pick 5 and you win. The game does get a little more complicated if you include an opponent. So for example, in this tree, first it's your turn, you get to pick left or right, then your opponent gets to pick left or right, and finally you get to pick left or right again. What is your first pick? And suddenly it's no longer trivial. It's no longer trivial to say, of course we need to go left, or of course we need to go right. We need something smarter to actually decide what to do here, especially if you want to put this all into an algorithm and let the computer pick. So one algorithm we can use in this case is the minimax algorithm. And if you want to implement this, the thing you want to do is you want to minimize the maximum score you can get when it's the opponent's turn, and you want to maximize the minimum score when it's your turn. And with this you can simulate perfect play. So what does this look like if you want to play this simple tree game? So back to our tree game. First we analyze the bottom row, and it's the opponent's turn. So the opponent wants, it's our turn, and we want to get the highest number. So we can just fill these in. So between 3 and 5 we pick 5, between 9 and 2 we pick 9 of course, between 6 and 8 we pick 8, and between 4 and 1 we pick 4. Then we go up a level, and the opponent obviously wants us to have the lowest possible score. So the opponent between 5 and 9 will pick 5. And between 8 and 4 the opponent will pick 4. And when it's our turn again, we again pick the highest one. So we pick 5, and the path we end up with is all the way down. If both players play perfectly, this is what we'll end up with. If one of the players makes a mistake though, if we go towards the 5, but the opponent goes towards the 9 because he wants to maybe steer us towards the 2, then we pick 9 and we win. So how would you program something like this? Turns out this code is very, very simple to implement with just one recursive function. In Java it looks something like this. The input is the starting node, and there's a boolean if we are minimizing our score or maximizing our score. And there are two things. If we are an end node, we just return the value of the node. And other than that, we loop over all the children, and we either maximize or minimize the score according to the boolean in which level we are. And then we return the score. And this is very simple, and it's easy to understand. If we look at some new terms from this game, we can see it has a branching factor of 2. What does this mean? This means that at every position, it splits into 2 different options, and this whole game has a depth of 3. So there are 3 possible decisions you need to make. And this game has perfect information. So you know all the options the opponent has, and there's no random in this. Of course, you don't know what the opponent is going to do, but there's no chance, there's no rolling a die or whatever. So let's take this game and turn it instead into an actual game. So what do we need to do? which factors can we take out from this? What do we need if we want to create a program that plays a game? First thing we need is a way to generate all the valid moves and put this in a tree. The second way is to, all the way to the bottom, assign a value to the nodes. And next, we need a way to pick a path. And like we just saw with Minimax, we can create an optimal path in this tree. So noughts and crosses, or if you were Dutch, butter, cheese and eggs, which makes no sense at all to me, because noughts and crosses totally describes the game. Butter, cheese and eggs is just random shit. This is an actual game you can play. I think everyone has already played this. So what does the tree of this game look like? Well, first you start with an empty board, and then the first player gets to put one cross in there, and there are 9 possibilities. After that, the opponent gets to put his mark in there, and there are 8 options left, and this quickly becomes a rather large tree. But this tree isn't very large for a computer. It's very easy to generate all the options and just evaluate them. So this is the game tree. The second thing we need is we need to assign a value to these options. And it turns out it's very easy. If you win, you assign a 1. If it's a draw, a 0. And if you lose, a -1. And this is enough. There's no half point or whatever. And you can generate this entire tree, start at the bottom, assign wins, losses, and ties, and then go up. If you do this with Minimax, well, first, this whole game has a branching factor of about 5. So first there are 9 options, then there are 8, then there are 7, there are 6. Divided by 9, on average, in every step, there are about 5 options left. The maximum depth is 9. Some games go to the end. Other games are, you can lose within 5 or 6 steps. And if you generate everything, which a computer can easily do, and you assign these values, and you remove all the symmetries, then there are 138 terminal positions. 91 of them is a win for for X, who starts. In 44 cases, it's a win for the opponent, and in 3 cases, it's a draw. And it turns out, if you apply Minimax to this, so you both play perfectly according to the rules we just saw, you'll actually end up in one of the draws. So if you play this game perfectly, it's always a draw. If one of the opponents, or if you or the opponent makes a mistake, then it's possible to win. Which is very weird, because there are a lot of terminal positions, but you can still steer it towards a draw every time. Let's move on to another game, a bit more complicated game. Chess, or should I say, the noble game of chess. What would a tree look like for a game of chess? Well, again, we start with a chessboard, and then there are all the valid first steps. Turns out in chess there are 20 valid steps you can take when you start. After that, the opponent can do 20 steps. So it's very easy to see that this branching factor, which in Tic Tac Toe was on average 5, in chess it's already 20 times 20 times. This is a very large tree. Also, the game of chess isn't over in 9 moves. Well, it can be, but most often it's not. It can go on for 40 or 50 steps. So this tree is enormous. And one of the things you can see how big this tree gets is if you run a perf. This is a performance test for chess engines. So this is what it looks like. If you start at the top, there's just a single node. The second step, there are 20 different nodes because there are 20 options you can take as a first player. After that, the opponent can do 20 moves. So it is already 400, 20 times 20 options. And this number quickly grows. So if you go in the tree, if you go 6 deep and you generate every possible outcome of this tree, you are already at 190 million different nodes. And there are a lot of captures, there are a lot of en passant moves actually. You cannot castle yet, you don't have any promotions yet. There are a lot of different checks you can make, and there are even after 4 moves, there are 8 possible checkmates where you can actually checkmate your opponent. And this number also quickly grows. These tables are used for 2 things. One is performance testing, so how quickly can your chess engine generate all these valid moves? The second thing is, it's like a perfect integration test, because if your chess engine, I wrote my own chess engine just, basically because I wanted to write a chess engine and I wanted to understand how this works. So you implement all the rules of chess and then you run this table, which is simply generate all the valid moves, then for all these moves generate all the valid moves, and for all these moves generate all the valid moves. And the first time you write your chess engine and you think you're done, you've implemented everything correctly, and you run this table and you go into maybe 10 deep, and there's this number which is 190,060,322 valid moves. And it turns out you're missing 1 or 2 moves, which is horrible to find, but it's the perfect way to test if your chess engine is valid. So, the game of chess. This search space is very big. This table, even after 6 steps, is already at 190 million different possibilities. And this is not even everything. So you're unable to check everything. With Tic Tac Toe, you can just generate this table. But chess, no way. The second problem you have with chess is how do you evaluate a move? We cannot go to the end. So we have to stop halfway, and we have to assign a value to this. Well, there are a couple of things you can do in chess. So one thing every chess engine does is that it counts the pieces. If you have a queen, that's a good thing. If you've lost your queen, that's not a good thing. The second thing you can do is that you can evaluate the positions and the liberties. So if you're, for example, in the center of the board and you have a lot of free space, that's a good thing. If you're all the way in the corner, that's probably a bad thing. So if you want to write a good chess engine, then you have to have some kind of evaluation function that determines who's winning and how strong your current position is. There's a problem though. There's always a horizon problem. Because we can't calculate all the way to the end, we have to stop somewhere. And perhaps this move doesn't look very good. But maybe, just maybe, you can do some checkmate move right after that. So maybe you sacrifice your queen and then you win. Because the next move could be a genius move. But if you stop evaluating at sacrificing the queen, it looks like a very bad move. So your chess engine stops there. That's a big problem. Also, if you go into this tree and you want to evaluate everything, it's very slow. So you need to speed this up. And one way to do this is with pruning. And pruning is, snoeien in Dutch, is that you cut branches from a tree. There are 2 types of pruning. You can do forward pruning, which is a bit risky, and there's backwards pruning, which is mathematically safe. So what is forward pruning? If a particular move is too bad, for example, after a couple of steps you sacrifice your queen, just stop evaluating. You are probably never going to play this. It's a bad move, and we don't have to go into this tree and look at all the options after that. We just stop. But like I said, this has the horizon problem. If you stop and maybe one step deeper you can make a checkmate, you won't be able to find this. The second thing is, if a move is too good to be true, also stop evaluating. So if it's opponent's turn and the opponent sacrifices his or her queen or gives away a checkmate, that's probably not going to happen. The opponent is probably smarter than that. So don't evaluate all of this. But, like I said, pruning is dangerous. That's brutal. There's also a safe way to do pruning. a mathematically safe way to do pruning. And this is called alpha-beta pruning. And this is actually an addition you can do to Minimax. So if you want to play Minimax, you first evaluate the first thing and you go all the way to the end. So first we have a minimizing move and then we have a maximizing move, and somewhere we find this tree. We get a score of 3. We're not done yet. We need to do something else and we evaluate further, and this maximizing move below that we get a 5. This is a maximizing move, so we pick the 5. And this gets propagated up. We have this 5. Now we evaluate another part of the tree, and we get a 9 there. And it turns out, at this point, we can stop evaluating, because there's a minimizing move, and there's already an option for us to get a 9. The opponent will never allow this. So even if the number below that, next to the 9, if that becomes a 1, for example, well, we are maximizing, we want a 9. So this number will never go down. And because above that we already have a 5, it doesn't really matter, because it's a minimizing move. So no matter what happens, even if the number grows, we're not interested in it, because it's a minimizing move. The opponent will always steer us towards the 5. And this also works the other way around. If the numbers were, if it was a maximizing move for us, and there's a smaller value, we can cut this entire tree from our application, because this will never happen in perfect play. So, this is the code we had earlier for the Minimax. But if you want to make a very smart and very fast chess engine, we can just tweak this code a little bit to also have alpha-beta pruning. This is basically the same, but I've hidden some things. The first thing we need are 2 values. That's the alpha and the beta value. The second thing is actually in the recursive function we also need to pass in this alpha and beta. When we maximize and minimize, there is this, we also need to maximize and minimize the alpha and the beta, obviously. And we need to include this stop criteria, where we, if beta is smaller than alpha, we can just stop evaluating. And just with these simple lines, you can greatly increase the speed of your Minimax algorithm, because you're pruning away this tree in a safe manner. Yeah, and this makes for a very efficient chess engine. I actually wrote a small chess engine which knew all the rules of chess, and it implemented this alpha-beta pruning search algorithm, and I wrote my own little evaluation function for which pieces do we have and where are they located, which was not very sophisticated, but it worked. And because the computer is very fast, I was actually able to make this chess engine in about a week, and I let my colleague, which is a very good chess player, play against this chess engine. He is an ELO of about 2200, and my simple program was able to beat him in chess, which for him, he was already playing chess for 30, 40 years, and I was just programming for a week. That was a bit tough for him, but yeah, it works. So, if you want to play chess using a computer, what do? We need a way to generate all these values moves, so we need to write our own chess engine. To evaluate the nodes, we can just count the pieces or some other smart thing, which is relatively easy in chess. If you look at a board, it's very easy to say this white is winning or black is winning. It's very, yeah, there are certain rules you can apply there. And we need a way to pick our path in this tree. And you could use Minimax, but it's better to do alpha-beta search here, where we do the pruning in a smart way. And this is just a little bit faster. Like I said, the game of chess, it has a much higher branching factor, 35 on average, it turns out. And an average chess game goes on for 40, 50 moves, maybe even 100. But this is way too big to actually to pre-calculate in a computer. But it turns out that writing an evaluation function is relatively easy. It's relatively easy to say who's winning or who's not. And a very good advanced chess AI can easily look 20, 30 moves ahead. And this is more than enough to beat a human. So in the last 2 decades, chess engines have become so good, you're unable to win as a human. Even the best grandmasters, they have absolutely no chance. So that's easy. Now we have this formula where we just plug in some things. We have a pretty standard search function. We have this evaluation function, and we make a tree out of it. And we can beat any game, right? So what's so special about the game of Go? So something about the game. It's a board game where you place stones. You've got black stones and white stones. And it's a 19 by 19 board. And yeah, there's these black and white stones. And your goal is to place them and to surround an area and actually capture a part of the opponent. So you want to surround some area and then that area is yours. Which sounds very easy. It may be even easier than chess, because in chess you have all these different pieces. This is just 2 stones, very simple. But there's a problem here. And that's the complexity. Because Go has this big board, it has a very big branching factor. So if you start, you can place anywhere on the 19 by 19 board. And on average, there are like 250 okay-ish moves you can do. The second thing is, a typical game of Go goes on for 300, 400 moves. So if you want to calculate this, it's 250 times 250 times 250, 300 times, which is a ginormous number. But still, this is something computers are very good at, is just doing the same thing over and over again. The last problem, though, is maybe the biggest problem. There's no evaluation function. Even the best players in the world, you can show them a board, and they can say, well, it feels like white is slightly winning, but I can't really explain why. And it's very hard to actually program feelings. So in chess, you could just say, black is winning because he's up a pawn. In Go, it feels wrong. And maybe you're surrounding an area and you're a third of the way there, but maybe you will never get that. So we cannot really count it. So, and there's all these moves. This is the number of moves that you can make in a chess engine. And the amount of positions, the entropy is actually bigger than the amount of atoms in our visible universe, which is a lot. So how can we make something that plays Go if we're unable to use this alpha-beta pruning or minimax? Or the whole problem is that we don't have an evaluation function halfway. We can't just stop and say this one is winning or this one is winning. Up to a couple of years ago, the best way to do this was using a Monte Carlo tree search. And why a Monte Carlo tree search? In Monte Carlo, they do a lot of Formula 1 racing. Nothing to do with Formula 1 racing, but there's one famous corner, and that's the casino corner. And that's actually where Monte Carlo comes from. It comes from the casino. So what do you do in Monte Carlo tree search? You just pick a node, and then you play randomly to the end. How is this helpful? Well, for example, if we have 10 different options. So for the first option, we go there and we play 1,000,000 times until the end, and we look at who wins. Then for the second option, we also play randomly 1,000,000 times to the end, and then we do that for all possible moves. This kind of gives us an estimate on how good this move is. So we don't have to stop halfway. We don't have to evaluate halfway and just stop somewhere. We just go to the end. We do it a lot of times, and then we look at these numbers. And this gives us an indication of how strong a certain move is. And up to 2015, this was the current state of Go AI. And experts said it will probably take 10 or 15 years before a computer can even beat a professional Go player. 1 year later, though, AlphaGo turned up. And AlphaGo was kind of a shock because it didn't work with all these algorithms we've seen before. It did something entirely new. So AlphaGo is based on neural networks. I probably don't have to explain what a neural network is, but here's the definition. A neural network is a computer model designed to simulate the behavior of a biological neural network of your brain. So let's just quickly take a look at what a neural network is. This is the website. Oh, this you cannot see. Where are you? There you are. Oh, this is going to be tough because I cannot see what I'm doing. Okay, there it is. So this is the website of TensorFlow, and you can actually build a small neural network here. So in this case, it has some input data. It has some blue dots and some orange dots. And this here in the middle is our neural network. This neural network has, in this case, it has an input. In this case, it has a vertical line. And we can also have as input a horizontal line. And there are some other things we can use as inputs. And in this case, we have one line, and we have one single neuron. And this neuron determines the weight of the input. So in this case, it's a vertical line, and this weight actually changes from left to right where this line is being placed. Let's just run it and see what it does. Well, using this input, it's very easy. It just puts it in the middle, and then it splits the data in two, and it actually is successful in solving this problem. But if we take, for example, a different problem, in this case, all the blue dots are in the middle, the orange dots are on the side. If we would just give it this simple input, it would be unable to do this because it's just moving the line left to right. Now, we can actually give it another input. So in this case, we have two inputs into a single neuron, and it actually is combining now the two inputs into one output. And if we run it, we can see it's a little bit smarter because it can now not only move it from left to right, but it also has an up and down into this. So it actually can change the angle of the output. But this is still by far not enough to actually solve this problem. If we add another neuron, now it's able to basically combine two of these lines. And by combining two of the lines, it's better at solving this problem, but you can see it still has this small blue area where it has orange dots. And it turns out that this problem can actually be solved by just 3 neurons and these 2 inputs. If you let it run for a little while, it actually finds a small triangle in the middle of the blue where it can separate out this data. So that's, in a nutshell, how you can use a neural network. Give it some inputs, it has some weights, and these are actually combined into the output. So if you want a very smart neural network, what do? Well, you can say, just give me a lot of inputs and a lot of hidden layers where we just pass the data. And you might think this is a good idea, but it turns out that it's actually not, because it takes way longer for it actually to solve this. And if you can see the weights which are displayed at how big these lines are, it uses just a couple of these neurons actually. It's not using the entire network. So bigger is not always better. So let's go back to the presentation. This should give you some idea of how a neural network works. But if you want to learn more, you go to the TensorFlow website. You can play with this web example, or you can actually put this code, download these libraries, and actually program against these libraries. If you want to use Java, there's Deep Learning for J, which you can use to build these things in code and actually run it. And other popular neural network libraries are Caffe or Torch or Theno. There are a lot of them. So, how did AlphaGo use these neural networks to solve this simple Go playing algorithm thingy? Turns out they did a lot of things actually. So, what kind of neural networks did they use? They used a convolutional neural network. This is where you take the input, you break it into smaller pieces, and you use this small piece as input layer. They used supervised learning, where you give it some input and you tell it if it's doing right or wrong. And it's not even that big. They used 13 hidden layers, but these layers are very large. So, the first neural network they learned was called the Supervised Learning Policy Network. They gave it the input of 30 million amateur matches, and they told it, given this particular setup, predict the next move that's going to be played. And if the neural network was correct, then you say, well done, you have to learn this. And if it's not correct, you smack it around and it has to learn something new. And the result is that this neural network was able to correctly predict 57% of the next moves. Which doesn't sound very good, but yeah, most of the time it's correct, so that's probably a good thing. Then they took this network and they copied it, and then they gave it a new goal. So instead of predicting what the amateur matches do, we want you to pick the best move. And to do this, the network played itself 1.2 million times. And this took just a day, but they were using tensor, what's called, these TPUs, tensor processing unit, which could do this in hardware very fast. And then they took this neural network and they pitted it against Pachi, which at the time was one of the better Go AIs. And without doing any search, just given the current situation, what would be the best move, it was able to beat Pachi 85% of the time. So after just a couple of days of programming, they had something that was able to beat one of the best computer programs 85% of the time. So by this point, they could have just stopped and said, well, we've done something amazing. But this was just getting started. Then they said, well, if 2 neural networks isn't enough, we have to find to make a third neural network. So what did they do? They created the fast rollout policy network, because the second network, every time you query this network, it takes about 3 milliseconds. This doesn't seem like a lot, but it's way too slow if you, for example, want to include Monte Carlo search, where you go randomly to the end, or in this case, use the network to predict to go to the end. And 3 milliseconds is way too slow. So this network is actually, again, a copy of the original network, but they've squished it and made it much smaller and much faster. So they lost information. It's not as good, but it's kind of doing the same thing, but it's very fast. In this case, it's doing every evaluation into microseconds, which is about 1,500 times faster. And yeah, so a third network. So if you were Google DeepMind and you want to beat the best player, what do? You make a fourth neural network, obviously. And for this neural network, they took the same 30 million matches they had before, and instead of asking it to predict the best move or the next move, just we ask it the question, who do you think is winning? So is white winning or is black winning? So initially, when they gave it these 30 million games and they let it run, it had an error of 0.37, where 50-50 would be random. But after doing the same thing again, where it has self-play and it's learning from itself, the error came down to about 23. And then they decided, how do we test this network? Is it actually doing something useful? Well, we can just give it a board, Then we generate all the valid moves. And for all these moves, we evaluate them and we see who's winning. And based on this, we just pick the one where we are winning mostly. And this was actually, just this network was able to beat the strongest known AI. Without any tree search, just one single step deep, we evaluate, we generate all the moves, we look who's winning, and we pick the one where we're winning most. So DeepMind by now has these 4 neural networks, and how is it actually going to combine this into AlphaGo? The first thing is they took this policy network and they used it to look at what are the current best moves. So instead of considering all the moves, it would just consider the best moves. So this is already pruning away some of the bad moves which we don't have to evaluate at all. For those moves, it would use the value network to double check which of these moves give us the best chance of winning. And after that, it would use the fast rollout network, which could quickly go to the end, but not with random moves, but with good moves, and then use the Monte Carlo tree search to give a better and better estimate on how good each move is. And they were already beating the best AIs, so what do? You set yourself a new challenge. We're gonna play Lee Sedol. And Lee Sedol is arguably the best Go player of this decade, maybe all time. So, best of 5 games, the winner gets $1 million. Just to spice it up a little, just to Lee Sedol really tries the hardest, because, yeah. The Challenger is a distributed version of AlphaGo. It's using 1202 CPUs, 176 GPUs, and as you can see, it's not using TPUs running. It's being trained with TPUs, but actually running, it's not. And yeah, the whole world is watching. Lee Sedol in one corner, AlphaGo in the other corner. And what is going to happen? The entire world didn't really expect much, especially in the eastern counties. They were pretty convinced no computer would be able to actually get close. Google said it had something interesting, but hey, come on. Experts even said it would take 10 to 15 years. And this is what happened in the first game. After just 102 moves, this is actually AlphaGo's minion, and AlphaGo's minion is now placing a move, and this is the reaction of Lee Sedol. His mouth literally dropped, and he froze. He froze for maybe 10, maybe 20, maybe 30 seconds. Because now it's sinking in, he's actually going to lose this first game after 102 moves. And his world literally broke down. There's a documentary about AlphaGo, which I highly recommend watching this on Netflix. It's called AlphaGo. And you can see he really struggles with this because he never expected this to happen, and the whole world was watching him, and this pressure for him was very big. And you can see his world is slowly crumbling down, and he actually loses the first game. AlphaGo wins the first game. And nobody expected this. Then comes the second game. Lee Sedol, maybe it was the pressure, maybe he didn't perform very well. But I was actually watching this live, and there are 2 commentators actually commentating on what AlphaGo is doing. And this happened after just 37 moves. And as you can see, AlphaGo already played a move,
and this is
and
what
they're now finding out.
From the Google team was talking about is this kind of evaluation value.
That's a very surprising move.
I thought it was a mistake.
Well, I thought it was a quick miss, but
A clicko. And if we were at online Go, we'd call it a clicko.
Yeah, it's a very strange. Something like this would be a more normal.
And now they just continue evaluating what maybe should be a normal move, but yeah, they can't really understand this move, and it's very hard for them to explain what's actually happening. And then they just continue with their normal evaluation, what a human would do. Because as the European champion at the time, Fang Yu, said, this is not a human move. I've never seen a human play this move. It's so beautiful. And this was the first time people were seeing the game of Go being played on a different level. Not a human level, but a better than human level. And they've never seen this before. AlphaGo won the second game. AlphaGo also won the third game. And in the fourth game, something incredible happened, which Guy Lou, which is Lee Sedol's arch rival, he said, this move was made with the hand of God. But he wasn't talking about the computer, because this was a very surprising move by Lee Sedol. And he actually was able to win the fourth game. And people were raving. They were celebrating. Humans haven't lost everything yet. We're actually doing great. Humans win. Yeah. Turns out there was actually a bug in AlphaGo, so we didn't. Yeah, it wasn't really because Lee Sedol was a genius. It was just some part of the tree wasn't being evaluated by AlphaGo. But in the end, AlphaGo won 4-1, and this game is now solved. So, conclusively, what does AlphaGo do? Well, what's so special? The special thing is nobody told AlphaGo what a good or a bad move was. We just showed it some moves, and it found out for itself what a good move and a bad move was. We didn't program in any rules of the game. We didn't program in that you need to capture an area or something like that. There is no evaluation function for AlphaGo. It just everything was figured out by itself, which is very powerful. Also, this isn't an expert system, because we didn't put in any of the rules. This system, which is now playing Go, could basically have played any game. And AlphaGo learned by watching itself and playing the game itself. And it used general machine learning techniques to figure out for itself how to win. And after this, there was a lot of response. So, for example, the Chinese government, the South Korean government, they invested almost $1 billion into AI research in the next 5 years. And yeah, it was very surprising that something like this actually worked. Nobody expected this. So what does AlphaGo, or what does DeepMind plan to do with this? There's actually a couple of things. So first, AlphaGo was trained using 30 million amateur matches. So this is human input. So it kind of knows how humans play Go. But instead, they've created AlphaZero. And AlphaZero didn't start with any human input. It just instantly started with self-play. So this allowed AlphaGo, for AlphaZero, to be much more creative, to play moves humans normally don't play. And after playing for itself a couple of times, they pitted it against AlphaGo, and AlphaZero was able to win 100-0, a clean sweep. So this kind of makes you wonder, have we been playing the game all wrong? Because if a computer is using the human game as input, it's not as strong as if we give it just everything as input. So, yeah, this is very surprising actually. And the thing that happened with chess, the game of chess actually really changed the last couple of decades, and people started playing in whole different, more aggressive ways, which humans usually wouldn't play because it's too complicated. But now we can do all this research and we can calculate all these different positions, and now we can actually find new interesting ways to play chess. And the game of chess has become more interesting actually, and they kind of think the same thing will happen for Go as well. Like I said earlier, AlphaGo, or AlphaZero, is a general purpose machine. It isn't especially made for Go. And to prove this, they also let it play chess, and they let it play a game of shogi. And it turns out it can also have superhuman chess and shogi abilities. Actually, the alpha version of chess is actually the best chess engine that there is at the moment. It's able to beat popular chess AIs like Stockfish and Ripka and other chess AIs. So what else can it do? The next thing they did was a thing called protein folding. Something that's very hard for computers and for humans to do is when you give a certain protein, it has the tendency to crumble up into a particular shape. And this shape is very important, for example, if you want to make medicine or if you want to find out how our body works. And AlphaFold, which is a version of of DeepMind's software, which has been trained on protein folding, took part in a protein folding contest, and they won everything. Like they blew the competition out of the water with protein folding, and it's actually been so very good that they now consider the challenge of protein folding, computing how proteins fold together, as a solved thing. Like we no longer have to guess. AlphaFold is just doing it correctly. If there are any StarCraft fans, they've also pitted Alpha's software with AlphaStar, and it was able to beat the best StarCraft spelers in the world. So even visual games can now be played using this software. Their ultimate goal, though, is DeepMind health. They want to innovate in hospitals, and they want to help people get better and fix diseases like Alzheimer's and predict things in that area. That's their main goal. That's what they want to do with these algorithms. And that was it. From playing games to actually solving Alzheimer's and other stuff. Are there any questions?
There are. Thank you for your talk. I think you inspired Bert-Jan because he has this amazing question. He has these dollar signs in his eyes. Would it be doable to train an algorithm to play other games, like, for instance, online poker?
The problem with online poker is there's a lot of chance involved. But I'm not sure. I'm not sure if they've actually used these algorithms to play poker. It could very likely work because there are just rules that are probably optimal to follow. But there's of course some chance involved. There's some bluffing, and that might make it a bit harder. But I'm pretty sure you can use these algorithms to play poker as well. I'm not sure if it's been done before.
Cool. I'd like to see that. So now basically, chess has been beaten and Go has been beaten. Have these projects now stopped, or are they still evolving this to make it even better?
Yeah, they're still trying to make this better. They haven't released a lot of things. So, for example, they've released some chess matches, which show that they're clearly beating every known AI. But this isn't something you can just download and use, for example. So people are now recreating it because they have released the research papers. So people are making their own little version of this. But like I said, the main goal is to not play games, but to actually progress humanity and actually solve diseases like Alzheimer's and, for example, give people better indications if they have some particular illness, then give better predictions what's actually happening with their bodies.
Yeah.
So that's their main goal, and that's what they want to solve mainly.
Eventually.
Yeah, but that's also how they want to make money. So that's the other side of the coin, obviously.
Enough. Now, in my spare time, I from time to time play chess. I'm terrible, but that's not the point. I also tried to play Go, and well, basically failed miserably. How are your Go skills?
My Go skills are non-existent because, yeah, it's a complicated game, and nobody wants to play with me. That's basically it. I do play a lot of chess, mostly with my son, who's 6, and I can beat him. But even that's getting harder. So that's my own little neural network.
Nice.
Yeah.
And have you also tried pitting your AI against other AIs to maybe see what its official ELO rating is?
Yeah, I tried that. There's a particular format. If you implement this format, you can just hook up other chess engines.
Oh, cool.
I think it was about 1600 ELO, which wasn't that good as my colleague, but for some reason I was able to beat him. But maybe it was the stress and other stuff that actually caused him to lose. I played it myself. It was actually very easily be able to beat me because my own rating would probably be 500 or 600 because I'm a really bad chess player.
Yeah.
So, yeah.
Cool. Can we try to play it? Is it available online? Can we see if we can beat it?
Yeah. So, like I said, my own chess engine is very horribly written and it's on my machine. AlphaGo itself, you can't play it online, so there's no way to actually play it. But they did release a lot of matches, and there are, if you, for example, look at YouTube, there are these very famous chess players who are actually analyzing all these games and finding new ways and interesting ways AlphaGo is actually playing chess and Go, for example.
Cool. Okay. Thank you. That's it.
Cool.
Thank you for the talk.